that perhaps did not receive as much fanfare, but it is undoubtedly equally profound. And that is how quantum mechanics was supplemented and made more complete by quantum field theory, or QFT. It is the basis of the best theory we have in physics today to explain nearly everything, called the standard model of particle physics. What is quantum field theory? Why is it necessary? How is it different than quantum mechanics? That's coming up right now. Classical mechanics has been and continues to be used to explain many phenomena that we can observe. Consider a planet orbiting a star. We can use Newton's laws to model it fairly accurately. If the planet were to somehow lose its kinetic energy or slow down, it would spiral into the star and collide. Now consider something conceptually similar. An electron orbiting Newton's laws to model it. Instead of the attractive force of gravity for the star and planet, the two objects' electrical charges keep it bound together. This is where classical mechanics fails because, as we know from Maxwell's laws, an accelerating charge creates electromagnetic radiation, and the constantly changing direction of the electron creates an acceleration. This means the electron would constantly give up photons, losing energy in the process. It would thus spiral towards the nucleus and collide. But we know that no such thing actually happens in reality. Atoms are stable. An electron does not crash into the nucleus. Why? Because we were using the wrong tool to describe the model of an atom. It can only be in an orbit that is an integer multiple of a minimal quanta, and its lowest energy state is the lowest orbit that the electron can have. It cannot be lower. This minimal quanta, by the way, is proportional to the Planck's constant. In Newtonian physics, we think of objects as discrete particles having very specific and measurable properties, such as a mass x, momentum y, and position z. In quantum mechanics, our objects are wave functions described by some completely different mathematics. This is shown by the Schrödinger equation, which is perhaps the most important equation in quantum mechanics. Here, the location of a particle is unknown until the moment of measurement. We cannot know where it is beforehand. We can only know the probability of finding it at any specific location. Prior to measurement, the wave function depicts a kind of smearing out of its location. It has some problems too. There are some things it cannot explain, and we get the wrong results, just like when we tried to explain the electron's orbit with the classical formulation. First of all, quantum mechanics is not relativistic. That is, it will give you wrong results if the quantum object is moving close to the speed of light. Schrödinger's equation simply doesn't obey Einstein's theory of special relativity. The practical result of this is that it doesn't incorporate a speed limit, the speed of light, needed to make causality work. For example, it allows for two measurements to influence each other faster than light. This would mean that there would be some reference frame in which the future could influence the past, breaking causality. A second problem with quantum mechanics is that it only tells you how a particle evolves over time. That is, how it goes about its business. It does not tell you how it is created or annihilated. So it can't account for things like beta decay due to the weak nuclear force, where a neutron transforms into a proton, an electron, and an antineutrino. It does not tell you how it is created or annihilated. So it can't account for things like beta decay due to the weak nuclear force, where a neutron transforms into a proton, an electron, and an antineutrino. In this case, quantum mechanics breaks down because it doesn't work if we change the number of particles. In the case of the beta decay I just described, the down quark of a neutron decays into an up quark, changing the neutron to a proton, and at the same time emits an electron and an antineutrino with a mediating W boson.
Shopping with your parents can be embarrassing.
Why would they sell jeans with holes in them? I'm going to speak to the manager.
Mom!
That hoodie is giving. You should get it. YOLO.
Thanks to the Chase mobile app, your kid can shop independently while you keep an eye on their spending. So you can go from
We can be twinsies.
to
How was shopping?
Quantum field theory explains things that quantum mechanics cannot explain on its own. So what is quantum field theory? Well, It's a mathematical framework that combines classical field theory. A classical field would be like a magnetic field as described by James Clerk Maxwell, special relativity, and quantum mechanics. There is a field for every particle of the Standard Model. So in our beta decay example, there would be a field for the down quark, the W boson, the up quark, the electron, and the antineutrino. All these fields extend out in all of space-time. In other words, the fields are always there and exist. Body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. So for example, the down quark field will always have some spontaneous creation of down quarks and anti-down quarks, which get created and annihilated almost instantly. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum, as long as that energy is put right back into the vacuum. This happens so quickly that it's as if nature doesn't register them as real measurable particles. We can visualize these fields as a kind of ocean. Just like the ocean wave has some turbulence, the fields always have a kind of turbulence, even in their ground state of minimal energy. This turbulence is due to the virtual particle creation and annihilation I just described. In these turbulent seas, if there's enough energy, a large wave can be created, which has some turbulence. The fields always have a kind of turbulence, even in their ground state of minimal energy. This turbulence is due to the virtual particle creation and annihilation I just described. In these turbulent seas, if there's enough energy, a large wave can be created, which can be measured. These are the real particles. So in the up quark field, for example, an up quark will be created if there's energy of 2.3 mega electron volts, or MeV, which is the mass of one up quark. Two quarks will be created if there's energy of 4.6 MeV. So a particle is nothing more than an excitation in this field. These excitations are quantized, not continuous. So the fields can only create particles in integer increments. They cannot, for example, have 1.5 up quarks, only 2 quarks or 3 quarks, etc. Now energy can be transferred between two fields via a mediating boson field. This is